Hi everyone, we are skipping Chapter 4, Section 7, which is on congruent triangle transformations. I'm deciding to do that since we're going to do an entire unit on transformations. So we're going to finish up with this last section, and it's called coordinate geometry, specifically coordinate triangle geometry. And in this section, we are going to use our knowledge of triangles, both isosceles and equilateral, and also other polygons like squares and rectangles, to find missing coordinates of vertices. We're going to do examples that are numeric in nature, where some of the given coordinates are just pure numbers. And then we're going to step up the abstraction a little bit and look at coordinates that are variable in nature. So those examples are going to be purely algebraic. This section tends to be a little bit difficult and challenging for some people, so I'm going to try to take my time with this. That might end up making a long video. I don't think I was very strategic in making some of these graphs extremely small. I probably should have spread this out a little bit more, so I'm going to try to zoom in on the video, but that might be a little bit difficult on your note handout, so hopefully you'll bear with me. All right, let's start out first with an isosceles right triangle. An isosceles right triangle is a triangle that has a right angle, and it has two legs that are congruent. So here I'm marking two legs congruent, and here's the hypotenuse. Of course, an isosceles right triangle then would be a 45, 45, 90, because we know that the base angles will be congruent. So I'm going to mark that. And if we subtract 90 from 180, we have, of course, 90 left. Divide by 2, those two congruent angles are going to be 45 degrees, respectively. Okay, so let's kind of zoom in here on this diagram. All right, so far I know that my vertex B is located at the origin, right here. And I know that this vertex A is located at -6, 0, and I need to find the location here of vertex C. So hopefully you can see that if A is located at -6 in the x dimension, well, the length of this side is 6, and it being an isosceles, right, the length here is going to be 6. So if I take a look at these numbers here, I've got 3 units being divided by 6, so hopefully you can see that our scale is 2 per unit. I'm going to try to use the language 2 per unit. Normally I would say 2 units per division, so I don't know, what kind of language that helps you. Actually, what am I doing here? 2 units per division. That would be how I would have learned how to say this. But I don't want to confuse anybody. All right, so both of our sides are 6, and if we take a look at this axis here, we're right on the y-axis, so it's pretty easy to see that the x location here would be 0, and if the length is 6, then the y location would be 6. Fair enough. When we're dealing with numbers, it's usually pretty easy. One thing I would ask you to do is write down any congruency, so we can say AB is congruent to CB. And I do think it's good to say that angle A is congruent to angle C. And the measure of those, let's say, equals 45 degrees. Let's go ahead and calculate the length AC. C squared equals A squared plus B squared. We're going to go ahead and use our Pythagorean theorem since this is a right triangle. And we are calculating that hypotenuse AC. So I'm just going to leave that as C. And we've got two sides of 6. So I've got 36 plus 36. And my C then is the square root of 2 36s, or 2 times 36. And you can see that my 36 here is a perfect square, so I'm going to go ahead and take that perfect square. And my hypotenuse length then is 6 times the square root of 2. So the length of this is 6 square roots of 2. All right, let's move on to an algebraic example over here to the right. In this case, our bearings here, our coordinates that we know are not numbers, although we do have numbers on the origin. But here we have a variable, b. So let's take a look at this example. Again, we see that it's an isosceles, right? Because the two legs are being marked as congruent. Let's go ahead and mark that down. AB again is congruent to BC. And of course angle A and angle C are congruent, and they're going to equal 45 degrees. Alright, so if we take a look at this here, we are on the x-axis, so for sure we know that that y location is going to be 0. And where is this x location? Well, if you look at above here, this length in the y dimension is b long. I know that because here I have a y coordinate of b. And that b is being divided by 1, 2, 3, 4 units. So each one of these is b divided by 4. We could say units per division, or I guess I'll just say b divided by 4. Yeah, I like units per division. Hopefully that doesn't confuse you guys. And if you look at it then, this would be, I'm just going to go ahead and put these down. That's b4, and then up here I would have 2b divided by 4. So this is 1b divided by 4. This would be 2b divided by 4, which is equivalent to b over 2. This would be 3b over 4, or 3/4 of b. And then, of course, a would be 4b over 4, which would just be b. And so if I have that, then I know that these are congruent, so I know this length here is b, and therefore my x location here is going to be b. Now let's go ahead and calculate our hypotenuse again, the length AC. So c squared equals a squared plus b squared. Now one of the things that's a little bit dangerous is my variable here is b, and we're also using b in our formula, but hopefully that's not going to confuse anybody. Each one of these sides in our triangle, the legs they're called, are b in length, so I've got b squared plus b squared. C squared equals 1b squared plus 1b squared is 2b squared. And if I take the square root of both sides, I end up with c equals the square root of 2b squared. And of course, b squared is a perfect square. So I'm going to go ahead and take that square root, and I end up with square root of 2 again times b. I think that is a very interesting result. If you look at some observations here, to the left, our numerical example resulted in a hypotenuse length of the side length times the square root of 2. Over here in our algebraic example, again, the hypotenuse ended up as the length of the side b, the legs lengths, times the square root of 2. Both of these are isosceles right triangles. That's an interesting observation to make. Alright, let's move on to equilateral triangles. First, I'm going to go ahead and zoom in on this numerical one to the left. Okay, we know it's an equilateral triangle because all three sides are being marked congruent. And of course, every equilateral triangle is also equiangular, so we know that we have 180 divided by 3 evenly, so each one of these are 60, congruent. Alright, let's take a look at what we have here. In one of these ordinate pairs, we have listed here vertex B at 5, 0, and vertex A is at the origin, 0, 0. So hopefully you can see without too much trouble that the length of AB is 5 units long. And so we know actually that the length of all of these are going to be 5 because it's an equilateral. Oh boy, that's a messy one. All right, and what else can we see here? We can see that 5 is being split up across 5 boxes or 5 units, so it's actually 1 per division, which makes life easy. And the easiest way here to see where then this location up here will be is to draw what's called the height or the altitude. The height of a triangle is the perpendicular from one side, from one vertex, I should say, to the opposite side at a perpendicular angle. In the case of an equilateral triangle, it lands directly here at the midpoint. So that is the midpoint. It's right in the middle, which means that these are 2 equal halves. And if I'm going to divide 5 by 2, I get 2 1/2. So this midpoint right here is at 2.5, 2 5/10, 0. And so if I just travel up, straight up that line here, well, this x dimension hasn't changed. That's also going to be at 2 5/10. I didn't leave myself a lot of room here on these graphs. So hopefully you can see that that x is located at 2 5/10. Now, where is this height? Where does that fall in the y dimension? So how long, in other words, is this on this scale? It's not 5. Remember this hypotenuse here, I kind of gave it away here. This diagonal line here is 5 in length. And the way we would find that height, this height of this red, is to take a look at, zoom in on 1/2 of this equilateral triangle and look at it as just a right triangle. So if I very carefully outline this and look at one on the left here, I have a right triangle that I can use the Pythagorean theorem on. I might just, to highlight that, I'm going to draw kind of a smaller sketch over here of the left side of this equilateral. So here, we don't know what this height is. I'm just going to call it h. But we do know that this side here is 2 1/2. And we do know the hypotenuse is 5 because that's one of the sides of our equilateral triangle. So I can use the Pythagorean theorem, c squared equals a squared plus b squared, to solve for that missing leg, that missing height. C squared, well, this time we know the hypotenuse, so we know that's 5 squared, and we know a is 2 1/2, and we're going to actually solve for the height. 5 squared is 25, and I like to look at 2 1/2 squared as 25 times 25. I happen to know that number is 625, but if I'm squaring this decimal here, I know I've got 2 decimal places, so it ends up being 6 2500ths. And I'm going to just kind of use my symmetric property here and move everything over. If I subtract 6 2500ths from 25, I get 18 7500ths. So if I take my calculator, I'm going to have to approximate that height, because 18 7500ths is not a perfect square, therefore it's an irrational number. That would be a decimal that goes on and on forever in a non-repeating pattern. So I'm going to just approximate it with a decimal, and my calculator tells me that's roughly 4 3300ths. So this height here, this height is going to translate directly into what that y coordinate is going to be. So this is going to be roughly 4 3300ths. The only other thing I wanted to mention, or have you write down if I didn't mention it, is that the height of a triangle, of course, we already know, is this perpendicular, okay? Straight down, perpendicular drop, let's call it. And the other word for that is called the altitude. You do need to know both of those words. Altitude is one of those, well, both height and altitude are one of those two words in the English language that have multiple meanings and very specific meanings in geometry. So we have to be careful with that. But we will, or you will definitely hear me use these interchangeably as I talk in the classroom. So height and altitude. Okay, great. Let's take a look at an equilateral triangle that's algebraic in nature. All right, moving over to the right. Again, we have an equilateral triangle. We know that because all three sides are being marked as congruent, and all three angles are marked as congruent. Again, these are all 60s. One of the vertices A is located at the origin, and we are given another ordered pair for vertex B, and that is located at 0, 2, B. So if we take a look at this scale then, we have 3 units being divided by 2B. So we could write that as, well, the way I would write that, I guess, is each unit is 2B, 2/3 B per division, per box, if you will. So we could think about that as this point right here on the y-axis would be 2/3 B, and then we would add another 2/3, which would give us 4/3 B, and then we would add another 2/3, which would give us 6/3 B. 6/3 B could be simplified to 6 divided by 3 is 2, or 2B. So hopefully you can get comfortable with dividing a scale algebraically. Okay, in any case, we see that the length of each of our sides is 2B. So each one of these are congruent. They're all 2B in length. We know that much. And let's try to figure out how we can find these missing coordinates for vertex C. Well, just like the previous example, we would draw the altitude or the height. So I'm going to go from that vertex C, and I'm going to go over to the opposite sides perpendicularly. And when I do so, I'm dividing that segment BA into 2 equal halves, because this particular point that altitude hits is the midpoint. I'm going to draw that. That's the midpoint. Okay, so 2B divided in half. What is 2B divided in half? 2B divided in half is going to equal B. So this location right here on the y-axis is B. And if I just follow that over here on the y here, I know that for sure that's located at B. Now what about the x dimension? So how do I find this? So I'm looking to drop this down here, and I'm trying to find this. I know it's a negative number, but how do I find that? Well, just like the previous example, we need to split this equilateral into these 2 congruent. You know they're congruent because of angle, side. We're going to split this up and look at 1/2 of it, and using the Pythagorean theorem, we're going to solve for that height. So if I kind of home in on the bottom here, maybe. I know my sketch is not very good. I'm going to sketch it over here. I do see some value in that. We're looking again for this height, or altitude. We have a right angle here, and this side here of half we said is b in length. And the hypotenuse we know is 2b. All the sides are 2b. So we want to solve for that height. So we've got our Pythagorean theorem, c squared equals a squared plus b squared. We know the hypotenuse already is 2b. And one of our sides is b squared, so I'm going to make a the height. 2b squared is 4b squared equals height squared plus b squared. I'm going to subtract 1b squared from both sides. 4b squared minus 1b squared is 3b squared. And then when I go to take the square root of both sides, I'm also going to use the symmetric property here. I end up with a height of square root of 3b squared. Of course, b squared is a perfect square. So I'm going to take that, and my height is square root of 3 times b. So I just calculated a length. Of course, a length is positive, but hopefully you can see that if I'm moving over here into the second quadrant, by the way, it's probably a good idea to remind people of what the quadrants are. Quadrant 1, quadrant 2, it goes counterclockwise. Quadrant 3, quadrant 4. If I'm going to move over here and I'm looking for this x, I clearly see I'm in the negative. So my x coordinate here is negative square root of 3 times b. Okay, now let's take a look at an example of square on the coordinate plane. I'm going to zoom in here on the lower left, and we have a square, but I actually should have written or marked these sides as congruent. This square is offset. It's covering the quadrant or overlapping quadrant 1 and quadrant 4. And let's take a look at a coordinate that we know. We know C, vertex C, is located at 10 minus 2. So this point right here is, oops, I don't want that. This point here is 10 on the scale, and over here is negative 2. So we've got 1, 2, 3, 4, 5 boxes equivalent to 10 units. So our scale here is 10 divided by 5, which is 2 units per division. And also in the y dimension, you can also see that we're 2 units per division. 2 divided by 1 box. All right, so fair enough. So right here we see that vertex C in the x dimension is located on x equals 10. So if I travel straight up to vertex B, nothing's changed there, so that's still x equals 10. And likewise, C from a y dimension perspective is at negative 2. And so vertex D is going to be exactly the same thing in the y dimension here. All right, if I just read my scale then, I have vertex D at 1 here, and we know that each division is 2. So that's 2, negative 2. If I travel straight up, vertex A is also going to be at x equals 2. And let's count the divisions. We've got 1, 2, 3, that's 2, 4, 6. So A is going to be located at 2, 6. And same thing for B. B is going to be located at 10, 6. Oops, I don't know why I just used blue. All right, so what's the lengths of our sides? The lengths of our sides are 1, 2, 3, 4. 2 per division, so each side is going to be 8. And another thing that we could do, and I recommend you do, is take a look at what the length of the diagonal of a square would be. Hopefully you can see that when you do draw that diagonal, we end up with two isosceles right triangles. They are congruent. The legs are 8 in length. And I would encourage you to find the length of AC on your own. And how would we do that? We'd use the Pythagorean theorem. Further, I'd like you to compare that result to what we looked at above on the isosceles right triangles. I think you'll see an interesting pattern emerge. All right, let's take a look now at a more algebraic approach here to the right. Okay. Again, we have a square, and this square, the center, exactly where the diagonals, in fact, would intersect would be at the origin, right here. So that's 0, 0. Okay, the only vertex we have information on is B, and B is located from an x perspective at 5B. So we have the crying, there is my dog Kane, he's crying. So I don't know why, it's probably dinner time. So we have 5B in the x dimension here, and that is split across 2 divisions. So 5B divided by 2 is 2.5B per division, or 2 5/10. Okay, so if we take a look at that, what does that give us? So if we move over here, we've got 2.5B, another 2.5B, that would equate to 5B. And I really haven't given a scale on the y, and this isn't, the y could be on a different scale, but since I have told you that this is a square, we would have to assume that the y scale is the same. So each one of these then would be 2.5B per division. So then at this y, it would also be 5B. So if I travel from vertex B straight down, nothing's changed in the x. So we would also say that that would be still located at 5B. But from the y perspective, we're now in quadrant 4, so y is going to be negative 5B. And if we travel from vertex C over to vertex D, nothing's changed from the y perspective, so vertex D is going to be located at negative 5B. But now we're also going into the negative here in the x dimension, so we're over negative 2.5B, another negative 2.5B. So in the x perspective, we'd be at negative 5B here. And if we travel from vertex D up to vertex A, nothing's changed in the x perspective, so we're at negative 5B on the x, but now we are up in the positive here, positive 5B in the y perspective. Okay, so if you look at this then, we've got side lengths here of 5B minus a negative 5B. Each side length would be a total of 10B in our square. And I would encourage you to do the same thing that I asked you to do in the last example, and that is go ahead and calculate the length of AC, one of the diagonals. That diagonal creates, again, 2 isosceles rights, 2 45, 90s, and it's a good observation to make on the resulting hypotenuse length there, that diagonal length. You'll see a pattern in all of those examples. Okay, great. Let's move on to the second page. Okay, let's take a look at an isosceles triangle. So zooming in here on the upper left, we have an isosceles. And we know that because 2 sides are marked congruent, and the base angles, of course, are also congruent. So we have two ordered pairs here listed. We have vertex B, which is, of course, in here, just reviewing the vocab here. This is the vertex angle, and that's located at 21, 3. And 21 in the x dimension is split across 1, 2, 3, 4, 5, 6, 7 units. So we would say 21 divided by 7 is going to be 3 units per division. And in the y dimension, we've got 6. So we've got 6 separated or divided by 2 units. So that would also be 3 units per division in the y. All right, so let's take a look at what we have here. We've got an off-centered isosceles here. And we'll take a look at first this length at the base. So if we take a look at this base, if we draw an auxiliary line, it's called, and in this case it's also the height. If we draw this height straight across from vertex B perpendicularly to the opposite side, that here would be our height, or we would also call that the altitude. And this, again, just like the equilateral, where that hits is the midpoint. So that would mean that this segment here, AC, is divided into 2 equal halves, or in other words, AD is congruent to DC. So that's how we would mark the given information. Okay, so let's first start at vertex B. If we travel along this altitude or this height and look at this midpoint D and its location, nothing has changed in the y dimension. So y would also be located at 3. And that base is sitting right on the y-axis. So the x coordinate would be 0. Now let's take a look at our scale. We've got 3, 6, 9, 12. So vertex A is going to be located, again, at x equals 0, y equals 12. And we have all of our ordered pairs for our location. So let's take a look at what the base length is. If we look at this whole length, we see that we're going down basically from 12 to -6. So this entire length would be 12 minus a -6. Of course, length is always positive. That would be 18 units long as our base. That would make each of these equal halves, then 9, if you will. All right, now let's look at the length of our sides. So to do that, we're going to, again, look at the Pythagorean theorem. I'm going to split this isosceles in 2 equal halves, or 2 congruent triangles. We know that they're congruent because of angle, angle, side. And I'm going to look at c squared equals a squared plus b squared. And we know we're trying to solve for this hypotenuse here. So c is what we're trying to solve for. One side of the leg, or one of the legs, is 9. And the height here, we know what it is 21. So c squared equals 81 plus 21 squared. If you use your calculator, you will get 441. So c squared equals 522. Or c equals the square root of 522. Now at this point, it's a good idea to simplify this. The way I would do that is just look at that 522 number. I see that it's even, so that's 2 times, let's see, 261. And then I'd look at 261. I'm going to first see, that's not even, so I'm going to add the digits together. 2 plus 6 is 8, plus 1 is 9. So I know for sure that 9 is divisible by 3, therefore this 261 is divisible by 3. So 3 goes into 26 8 times with a remainder of 2, and that would be 3 into 21, or 7. 8 plus 7 is 15. 15 is divisible by 3, so I know this number is also divisible by 3. 3 goes into 8 2 times with a remainder of 2, So this would be 29. I'm getting a little bit squeezed out here. So if I look at these numbers then, the square root of 522 is the same thing as 2, and I've got a perfect square here, times 9 times 29. So I'm going to put that perfect square first. 9 times 2 times 29. And that perfect square I'm going to take out. So C equals 3, which is the square root of 9. And I'm going to button back the other two numbers. 2 and 29 are both prime numbers, so I'm going to multiply those back together. I know I can't find any perfect squares there. So C then is 3 square roots of 58. So we have here the height is equal to 21. And the base is 18 units, and each of these sides is 3 square roots of 58 in length. And they are congruent. All right, let's take a look at an algebraic isosceles triangle. Over here, we have a tall, skinny isosceles, and I should have marked them as congruent for sure. Otherwise, you'd never know. And if the sides are congruent, of course, the base angles are also congruent. Now, the only thing so far that we're told is the location of vertex A. Vertex A is located at negative B in the x dimension and negative C in the y dimension. And so this is the first example where we have two different variables, one for the x and one for the y. And I thought it would be important to look at an example for that. So in the x dimension, we have 2 units equivalent to a negative 1b. So let's take a look at that division. So we've got b divided by 2 equals, 1/2 b. If you wanted to put that as, in terms of a decimal, you could. So it would be 5/10 b per division. And likewise, the same thing for c. We've got c in the y dimension being split across 2. So that would look the same, c divided by 2, and if you feel more comfortable with decimals, that's fine. I don't. I kind of like the fractions. Okay, so let's take a look at what we have here. Let's start with the base. So in terms of the y dimension, everything along this line has a y dimension of negative c. So we can go ahead and fill that in. For the point D here, that's located at negative c, as well as vertex C. And now let's look at from the x perspective. We have 2 divisions is negative 1b. 2 more would be negative 2b. And likewise, 2 more would be negative 3b. So we have all of these outlined here. Now let's look at the length here. From the perspective of length, we have 1b and 2b. So the length of our base is 2b. And when we drop this altitude or height, again, perpendicular, when we drop that, that is hitting that point D is the midpoint. So that would mean that CD is congruent to DA, 2 equal halves. If the entire base length is 2b, then each one of these is b in length. All right, let's take a look at this vertex angle B up above. So if we look at our scale from a y perspective, this is negative 1c. So this is 1c. Another 2 division will be another c. So this is 1c. Why don't we label that? 1c. Go up 2 more, 2c, and 3c. Maybe that'll help. So from a y perspective, this vertex B is located at 3C. And we've already found what it is from an x perspective. If we travel from vertex D straight on up, nothing's changed from an x perspective. So that's located at negative 2b. So just as we did before, if we want to find the lengths of these legs of our isosceles triangle, we're going to look at half of this. One of the congruent, these are congruent triangles here. And we're trying to solve for the hypotenuse, C. This is a little awkward in that, in fact, I'm even going to erase that. One of our variables is named C, and it's not the hypotenuse. So I'm going to rearrange. Of course, normally our Pythagorean theorem is c squared equals a squared plus b squared, but I'm going to just rename it hypotenuse squared equals leg 1 squared plus leg 2 squared, just to keep everything straight, that we're not mixing variables with variables in a formula. So our hypotenuse here, squared, is going to equal one of the legs, which is b. I'm going to square that. And the other leg is our height here. So let's take a look at our total height. So above this x-axis here, we have a total height of 3c, and below the x-axis, we have another 1c. So the entire height is 4c. Let's plug that in. So the other leg is 4c. We're going to square that. So our hypotenuse squared equals b squared plus 4c squared, which is 16c squared. And therefore our hypotenuse, or the lengths of these isosceles triangle, is going to be the square root of b squared plus, this is a 1 here, 16c squared. That's a little awkward, but that is the length. So it is an algebraic expression. Each of these sides is b squared plus 16c squared. And over here, same thing, square root of b squared plus 16c squared. And just leave it like that. Okay, moving on. We're going to now look at some rectangles. First, a numerical example. We have a rectangle. A rectangle has 4 equal angles, so it's equiangular, and the opposite sides are congruent of a rectangle. We're given one of the locations of one of the vertices, and it's vertex A, and it's located at negative 2, negative 2. So that would suggest here that it is 2 per division. That's our scale. 2 units per division. Okay, so let's start out at vertex A. If we travel up to vertex B, nothing has changed from an x perspective. So x will be located also at negative 2. And if we're at 2 per division, then the side here would be 2, 4, 6. So this is 6, and of course opposite sides are congruent. So if we look above the x-axis, we've got 2, 4. So from a y perspective, vertex B is located at 4. Let's keep traveling clockwise. So if I travel over to vertex C, nothing's changed from a y perspective. So that's located also at 4. And let's count the scale here to find the location of C. We've got 2, 4, 6, 8, 10. So C would be located at 10 from an x perspective. And then travel down to vertex D. Again, nothing's changed from x perspective, so that will be also 10. And that will be located at negative 2 from a y perspective. And if we look at the remaining 2 sides here, we can count the boxes. We've got 2, 4, 6, 8, 10, 12. So we can take a look at this. And we could find the perimeter, we could find the area from here. Of course, the perimeter is the rim, add up the outsides, which would be 2 times the length plus 2 times the width. Some people call that 2 times the base plus 2 times the height. And then the area, we could count the boxes inside here. It's a 3 by 1, 2, 3, 4, 5, 6. Of course, each one of these are worth 2, so that would be 3 times 6 is 18 times, 6 times 12 would be 72, so you'd have to multiply both of those by 3. Or some people call that like length times width or base times height. So just realize that both of those formulas are the same. By the way, you could also go ahead and calculate the diagonal of this. You could draw the diagonal between vertex B and D, and you would be able to find the length of that diagonal using the Pythagorean theorem, because the diagonal would be the hypotenuse. Looking at a rectangle from an algebraic perspective, we have here again actually four variables this time introduced. So start with the one that you, start with any one that you want here. I'm going to start with vertex D. From a perspective of Y, I'm going to go counterclockwise. Vertex A is at the same location from a perspective of Y as vertex D, so that would be negative B. From a perspective of X here, if B is located at negative C, I'm going to drop right down. That would mean that vertex A is at negative C. From the perspective of X dimension, C and D are at the same location. So C is located at A. And this was really bad of me to use the same name of a vertex as a variable. I should not have done that. And then from a Y perspective, vertex C and B are located at the same, so that would be D. So if we took a look at the lengths, then we know the opposite sides are congruent of a rectangle. Whoops, I should have. And I have to differentiate between the sides. Let's take a look at the length here, the short length. So we have 1C going there, and we have 1A going here, and so this length would be A. I'm going to go ahead and write it A minus a negative C, so that would be A plus C. That's the length, and that would be the same up here. A plus C is the length there. And then the height, or I don't know, the width, I don't know how you want to describe these. We've got D minus a negative B. So we've got D minus a negative B. So that's D plus B is the length, and of course the same thing would be over here. So you could take these variables, these variable expressions, and you could find the perimeter. Say the perimeter equals twice the base plus twice the height. I could say the perimeter is 2 times A plus C plus 2 times D plus B. And likewise, I can look at the area. Area is base times height, or length times width. And I could say that would be A plus C times D plus B. So that would be a nice variable expression we could find. And again, you could also take a look at the diagonals if you wanted to. You could find the diagonal using the Pythagorean theorem, and because we'll end up with two congruent right triangles. All right, let's take a look at our final example over here. Again, we're going to go back to an isosceles right triangle, and I know this is an isosceles right triangle because I'm looking at the lengths here. That length is going to be 3A units long, and this length in the y dimension is 3A units long. Now, the goal here is to find the location of D. And if we do have this isosceles right triangle, if we draw this height or altitude here, and it is a height or altitude, I can prove that by checking the slopes, that the slope of BD is the opposite reciprocal of the slope of AC. And if we do that, we can definitely see that this would be a right angle given those slopes. Okay, so when we draw this height or altitude from this vertex B, which happens to be the origin, when we draw that, we are going to hit this point D, which is the midpoint. And that's the midpoint of AC. And so we can find the location of that midpoint in the way that we've done in the past. So you could kind of ignore this triangle here. We're just looking for the midpoint between two endpoints. We know how to do that. It's the middle, and it's the middle in both the x and the y dimensions. So the middle between two numbers is the average between those two numbers. So we could say in the x dimension, we're looking at the middle between the two x locations of the endpoints and the y locations. So here we have in the x 0 and 3a. 0 plus 3a divided by 2. And in the y dimension we have 3a and 0. And we're looking for the average there. So depending on how you like to look at numbers, I like fractions, so I would say 3a divided by 2, 3a divided by 2. But if you wanted to put 1 and 5/10, that would be fine too, if you like decimals. So this midpoint then is going to be located at 3 halves a, and that's the middle, exact middle, between A and C. So I'm going to draw AD congruent to DC. Thanks for listening. Hope this helps.